I guess I'll go there. Yeah, I'll probably just order it.
Okay. All chromatography. Oh, actually, all chromatography. What types of chromatography are there? Gas chromatography. Ricky, another type of chromatography? Liquid? Another one, Kathleen? We don't have a machine for these, but there's other types. Yes, sir? Supercritical fluid. How about paper? Paper chromatography, right? Okay. So, have a bunch of markers. What do these say? Vis-a-vis, wet erase, non-toxic. Well, these guys must dissolve in what? Water. Great. Okay. So there's some water. Put a little mark on each one, right? Put it in the water. Oh, I have too much water in there. That's okay. Okay. Now, what I did is I put a line on. I have the black, got the red, got the blue, got the green, and then I have a permanent black. And it looks like the water's getting pulled up the paper. Why is that? Adriana, why is that? Capillary action. Yeah. And man, it looks like, I don't know if you can see it, but right? One of those dudes, looks like the blue one especially. Emily, what must be in the blue marker? Yeah, I gotta see it's facing Adriana. Yeah, there's must be several colors in there, right? Okay, you have to be an artist to really know what colors make what colors, right? That color wheel thing. But yeah, there's more than one dye in a lot of these. So, I don't know if you remember this from analytical, John. I think I did the same demonstration. And if you got a master's in business pretend from Our Lady of the Lake, you want to start up your own vis-a-vis company, but call it John-a-Viz, Big Bad John markers. They're going to be big, right? Big markers. They'll last forever, right? And why reinvent the wheel? Just see what the heck these guys are using for dyes, right? Because you know they're using the cheapest ones, the most available ones. They work great. Why reinvent the wheel? So what could you do? It's using paper chromatography to get all the, well, this guy looks like he might be pure, just one. But this guy has several in him. What could you do to get all these individual dyes? Just using a piece of paper and water. Yeah, but you gotta get a scissors, right? They're gonna, look, they're already separated out. That is pure yellow dye there. That's the pure blue, right? It works. Okay. So, looks like all chromatographic methods, Robert, separate the what from the what? Using our technical jargon.
Analyte from the...
Yeah, analyte from the...
matrix.
Matrix. Analyte from the matrix. Exactly. Okay, some more terminology. Anna, how about the next one? The blank phase. Now you can be talking about any type of chromatography, paper chromatography, GC, LC, all of them. The blank phase transports the sample through the blank phase. Mobile through the stationary. Excellent. Okay, looks like in our Sandy in this little setup here, what's the mobile phase? What's the stationary phase? Yeah? Yeah, paper stationary phase. Why is it working? Alice, why is it working? Yeah. Especially in that little blue dude. He's got really the only one that has something to separate, but why? Now, it looks like it's not working with this one because that's a permanent black. But on the others, it's working. Why is it working? Yeah, they're different colors, they're different molecules. They have different masses. Is this thing separating them out because they have different masses?
Yeah, so the lighter ones will go higher than the...
That's a good guess, but it's not right. She makes sense though. She's on the right track, right? Like the lighter ones get pulled up because they're lighter, right? Well, they all have to be soluble, otherwise they wouldn't be vis-a-vis, right? So that's a key. They all have to be soluble. Yeah, how soluble? Doesn't matter. They just got to be soluble. Concentration? Is this thing? If it was more concentrated, I bet the blue band would just be darker blue, the yellow band would just be darker yellow is all. It's not concentration. How is this thing working? Size. You have to look at paper through a what to actually see why? A microscope. Then you got the little fiber spaghetti stuff going on. It's exactly what it is. The technical jargon for this isn't really paper chromatography. Sounds a lot better. You could sell this. Size exclusion chromatography. Ooh. Right? But that's exactly what's going on. What stuff is going up first? The bigger or the... Well, you're on the right track. She was so close. In size, the smaller ones are getting up first. And all of them have to be soluble in water to some degree. Right? Smaller ones are whipping through that forest of spaghetti first. Okay. The bigger ones are, stuck in there, but we're not supposed to use the word stuck, Pablo. We're supposed to use an R word. The larger size molecules are what? Retained. They're retained. They're retained. Okay, they're retained more. Okay. Than the other ones. Okay. Elution chromatography. Is this elution chromatography, Ashley? An elution chromatography, I'm trying to think of the book. You'd have to go by the book to answer that question. Because in elution chromatography, you always have a mobile phase going through a stationary phase. Well, that fits this, right? That's all chromatography, really. Elution chromatography, your analytes elute from the end of the column. Okay. I think if you could just hold this upside down, it might match this better, right? In elution chromatography, there's a word called the eluent, and you always keep dumping it up on top, okay, and stuff just flows through. So I'd have to see the technical jargon to answer that question. I mean, my guess would be that it is, but I'm not technically continually adding mobile phase because it's just sitting there in a beaker. It has a constant amount of mobile phase. But technically I am adding it because it's being sucked up the paper. So I am really adding mobile phase. So my guess would be that is elution chromatography. But
the picture, they're going downward.
yeah, gravity is supposed to be pulling all this stuff through. So this blue stuff is just a beaker full of all your analytes. I guess your analytes are just A and B. So you dump it on top of this column, and this is just packed with something. And they just dump it on top. And they got to keep adding mobile phase, though. Otherwise, it's just going to stop dripping out. And then everything's just going to stay there. So you got to keep adding mobile phase up on top. Yeah. So these are technically be called your columns, and it's just gravity. They're physically holding them up and down, so gravity pulls everything out. Okay. So in this setup, what makes A and B go down the column? Gravity. Yeah. What's in there? Try whatever you want, yeah. Try whatever you want. Stationary phase is what's in the column. Some are going to be a lot better than others. How about a chromatogram? In this picture up here, there's a chromatogram, Ricky. Where's that?
I guess that's B. That time versus...
There it is, yeah. This thing. Signal versus time. That's our chromatogram. Right. what the detector's detecting. So it looks like, at what time would you say A and B are starting to separate you, Randy?
From the chromatograph?
Yeah. Let's see. Where are we at? This one.
Well, A starts at T3 and B comes out at
Yeah, the time they come out, but the time they're starting to actually separate. T1 or, I mean, or even, you could even argue for this one. Because right when you dump them on, they're starting to separate. You can't stop it, right? Why are they separating? Kathleen, why would you say they are separating? It could be size, right? What else could it be? Polarity is a good one. What would polarity have to do with anything? Using all the technical jargon, right? Like dissolves like. If this stuff is really polar, what's a really type of polar compound that we could put in here? What's that? Some kind of gel-like stuff, if not a solid, 'cause otherwise it's going to fall on through. I guess you could have a frit, but yeah, if it's a liquid, it's just going to get diffusion, right? It's going to be like adding a dye to water. So this really can't be a liquid. It needs to be fixed, a stationary phase. So what could it be that would make it kind of polar? Ooh, silica gel is polar. Why is silica gel polar? Has a lot of what groups? OH groups. These SiOH groups. So it's really polar, just like water. Like dissolves like. Anything that's polar is going to hang out more here than like how benzene or something, right? Let's go right on through. Okay. Where are we? Or what time does A come off the column? Yeah, it looks like T3. You go for, right, it's actually starting to come off the column earlier than T3, but you're supposed to pick the peak. And it looks like, is this thing, right, as it's starting to come off, be right down here, right, kind of move it up a little bit. It's starting to come off, and it comes off, right? Is it the same concentration throughout in that band? How can you tell? You're supposed to look at what? Is it the same concentration throughout? Look at the signal. Yeah. Look at that. It's most concentrated where? In the middle. Very most concentrated in the middle. It's like that for all bands. It's most concentrated in the middle. Let's see. B comes off the column at T4, right? Which one spends more time in the stationary phase, Adriana? A or B? Which one spends more time in the stationary phase? Ah, B, right? He comes out later. See if you remember this one from analytical. Oh, Ricky, he didn't have analytical with me. He landed pretty good. Which compound spends, A or B, spends more time in the mobile phase? Now, B hangs out longer in the stationary phase. That's why he's out later. But which one spends more time in the mobile phase?
How could it not be neither? I mean, they're both suspended in that mobile solution, no? Because the mobile solution is a solvent, right?
Yeah, you're just flowing it on through. But these molecules, they have to, what they want you to think of for this stuff is they want you to actually think of A or B, the little molecules going out of the stationary phase, dissolving out of it, almost like a precipitate, and sticking onto here, and then jumps back into the mobile phase and moves down. Whenever it jumps in the mobile phase, it has to move down because the mobile phase is moving down. So it's constantly dissolving in and out of the mobile phase. Okay? Or you can kind of think of it as being stuck for size exclusion, right? It's stuck. Mobile phase is flowing around it, right? Gets unstuck. Well, then it moves with the mobile phase. Gets stuck, right? Same type of thinking. You remember this? How do you explain this? Which one spends more time in the, not that one, this one. Which one spends more time in the mobile phase? You, Randy, you remember this? That's the answer. They spend the same amount of time in the mobile phase. Basically what he said. But why? Why?
Because the column's the same size.
Same size, same length. They all have to travel the same distance. And the only way you can move in the column is if you jump in the what phase? Mobile phase. So you have to, and when it doesn't matter whether you're A or B. If you jump in the mobile phase, you're moving down at the same rate because you're in the mobile phase, right? It's dripping out. Bloop, 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 bloop. So if you're in the mobile phase, you have to be moving down the column at the same rate as everything else. Doesn't matter what the analyte is. Okay. It's just that if you're B, it looks like, you jump out of the mobile phase more often for whatever reason. It could be because you're bigger, if this is size exclusion chromatography. It could be because it's more polar, like you're saying, if this was like a silica gel or a salt. Okay, something really polar. If B was polar. Does it look like there's more of A or more of B, Emily? Here's a hint. This is another trick question.
So then
Yes, Ashley.
back to 6.
Going back to 6, yes. That's fine.
So they both spend the same time?
In the mobile phase. Yeah, because that's the only way you can move down the column. And they all have to move the same distance. So it's, all right, just like an equation, speed is distance over time. Solve for time. I mean, they all have to spend the same amount of time in the mobile phase.
And this is like only before an elution chromatography.
Yeah, pretty much all types of chromatography we're going to be talking about is elution chromatography, where we have a mobile phase flowing through a stationary phase. Anytime you have really in general, a mobile phase flowing through a stationary phase, it's elution chromatography. And that's the only type we're going to be talking about. Paper. Yeah, I'm going to be working with a lot of paper. Okay. We were here. 7. Is there more of A or B? Why is it a trick question? No. Big bad? Depends on what? This is a hard question to answer until after you've had, some of you did use the UV vis, right? And you took spectra of some food dye, right? Who did the UV vis with the food dye? All right. Okay. Now, when you took a lot of absorption spectra, right? There were these broad things, right? And some different colors had different peaks. Okay. Could you have picked a wavelength, nanometers, on this plot? Because it's nanometers, and here's signal, and then you got this big, just like this, looks just like these guys, except a lot more lumpy, right? Could you have picked a wavelength down here, right, if this is a spectrum, that would be good for all these different colors? It may not be the maximum for them all, but there'd be some absorbance at every single, at that wavelength. Could you have picked one?
Yeah, I think so. Because I think they're mostly on this side.
Yeah. See, that's all you'd have to do for the detector. See where I'm getting at? You just pick that wavelength, and you monitor the absorbance at that wavelength. Now, some colors can absorb a lot better at that wavelength. Fine. You don't care. You just want to get some signal and make it work. So there may be a dinky amount of A, but Pablo's got it set up so that the detector is right on the peak of A. Peaks, right? So there can just be a little bit of A, but it absorbs a lot. And you're not on the peak of B. You're kind of off. But there could be a lot of B just for you to see a signal in the first place. So you can't tell. For 7, you don't know. You have to make a calibration curve to figure this out, to figure out the amounts of things. How about, Robert, are pure A and pure B obtained at the bottom of the column?
They better be.
You bet they are. Ultra pure, right? It's pure stuff. Anna, are these compounds, you stick a little beaker down here and you, right, starting right about at this, when you hit this, you're collecting A, and I take the beaker out, you put it down here. Don't have it in here, otherwise you're just collecting pure solvent. So you start this time where the signal's going up and you just collect it. Are these, the stuff you collected in the beaker here, is it more dilute or more concentrated? in comparison to up there? It's more dilute. Yeah. Consequence of all chromatographic methods. They're more dilute. You can't stop it. But it's pure. What's that?
It's
Pure but really dilute. Yep. Well,
Has to be something else there.
When it's pure, shouldn't it just be that substance?
well, think of it as you have all this solvent in there. 1 molar versus 2 molar, right? So they're both pure. You could both be in water, but one's 1 molar, the other one's 2 molar. One has more water than the other one. That's all it is. This just has more
Apparently water doesn't-
mobile phase, right? Yeah. You don't think of the solvent as an impurity, right? You don't think of the solvent as the impurity. Yeah. Because you could just let the water all evaporate off, then you'd have your pure stuff sitting right there. What else could the x-axis be? Alice, what else could we plot? We have a detector signal. We can't mess with him. But what else could this be? Instead of time, make it... Well, if it was concentration, you'd have to do some calculations to get it and everything. Distance down the column, that would be good, right? But then, yeah, I guess that would work. You have to have a detector everywhere. That would be kind of a job. So that may not work for our setup.
Maybe your research.
We're getting there. What else could it be? What could it be?
Johnson mobile.
And it's going to look exactly the same. It's going to look exactly the same. Make it be what? Amount of mobile phase. Because mobile phase depends on how much it's dripping out of there every minute. Right? Just figure it out. However much is dripping out per minute. And then this could be volume, like milliliters. Okay? Then it'll look exactly the same. Okay. Oh, someone asked too about goggles. If you need goggles, just ask. I can give them to you. Which compound A or B is more soluble? Now we're starting to play around more with technology, more with terminology. Pablo, which compound A or B is more soluble in the stationary phase? A comes out faster. Everybody agree? Here B. Why is it B on? You're agreeing with Adriana.
Yeah.
Well, they both spend the same amount of time in the mobile phase.
Yeah, but
B spends more time in the
it's different.
stationary phase. That's what you're shooting at. B spends more time in the stationary phase. So therefore, he is more soluble in the stationary phase. Like dissolves like. Which one spends more time in the mobile phase? Same time, neither, right? Which compound A or B is more strongly retained, Ashley, in the stationary phase? Yeah, again, B. It's just, we're saying the same thing and using different terminology is all. Okay. Are compounds A and B of homogeneous concentration, Ricky, throughout their respective purely separated bands? So they're looking at this thing, or you look at it down there.
Whoa.
Are compounds A and B of homogeneous concentration throughout their respective purely separated bands?
Wow. In the solvent?
What does it mean?
I would say that they are.
What does it mean, homogeneous concentration?
That they are consistent throughout.
Consistent throughout, same concentration throughout. If it was the same concentration throughout, you wouldn't get a peak though. You'd have it kind of go straight up, square, and then straight down again. All right? Yes, they're not. It's most concentrated where? In the middle of it, in the middle of that band. Okay. How would that chromatogram change, would you say, Randy, if the amounts of A and B were doubled? So at the very top of that column, we're going to just dump in twice as much. Just evaporate half of the solvent that's there, and make it twice as concentrated, run the whole thing through again, how would this change? Higher peaks. Does everybody agree? Could be wider, higher. Are they going to change? Is this little T3 going to change? It can't. That, I think, is the... Well, there's two real powers of chromatography. One is you get pure stuff at the end. The other one is these retention times. They always work. As long as you reproduce everything. The temperature, the column, right? That's about it, right? The length of the column, the mobile phase flow rate. As long as those separation parameters are the same, yellow is always going to come off at T3. Red is always going to come off at T4, whatever those colors are. Okay. And why is that really nice? Because then you walk in the lab, you have your GC or your chromatographic setup all set up, and you get paid, I don't know, $500-600 to run these blood samples for cocaine every day. You don't have to redo everything. You just shoot the blood samples. Oh, peak at 6.2 minutes. That guy's in trouble, right? You don't have to. I mean, you really do need to run standards and all that stuff again. But the point is it doesn't change. Okay. What is zone broadening? So I guess the question really is, why aren't these things straight up, straight down? Why is there some width here?
Because there's no concentration there.
Why is it fat?
That's really speaking.
Why do? Yeah, it's not the same. Let me ask that then. Why is it not the same concentration throughout? Why is it most concentrated in the middle? Why isn't it a homogeneous concentration? Now, it's pure. And why does it get fat? In fact, they did do kind of a good job with this. Look at how wide it is here, the band. Now look how wide it is. It's already separated. They could have stopped it right here and just chopped this column off, and you would have had sharper peaks. And they would have been down here somewhere, but it would have been sharper. Look how much they're not near as wide. As it goes further down the column, things get even wider. Why? What's that? Yeah. Yeah, they're definitely getting more diluted from the mobile phase, but it's called zone broadening. Why? Think about the molecules themselves. Yeah. No, they're definitely not. Why would this band get fatter as it goes down the column? Diffusion, yes. We're getting there. There's two types of diffusion. Eddy. Okay, start with one. Okay, eddy diffusion was one of them. What was eddy diffusion? Different paths. Some of these guys, you can kind of see the little holes here. Some of these molecules are going to have a shorter path. Some are going to take a longer path. Well, that's going to result in them spreading out more. Right. How do you spell eddy diffusion? E-D-D-Y. E-D-D-Y. That's one of them. Eddy diffusion. Different molecules take different paths, and that's a really good one for this because you can see the little dots. There's going to be long ways, and there's going to be short ways to get to the end. And the longer you're in that column, the more they're going to spread out simply because of eddy diffusion. Yeah, all the same endpoint, but they're going to spread out. The longer you keep it in there, the worse it gets. Eddy diffusion. One more type of diffusion. Longitudinal. Longitudinal. Kathleen, how do you spell that one? I'm going to get by with not writing anything today.
Oh, that picture is awesome. We show you pictures.
What picture?
It was on Cartoon Network.
We're going to get you a t-shirt.
Oh, longitudinal diffusion?
No.
No.
I'm always saying to Google it to people. All right. That's a good one for research. But spell longitudinal diffusion. Because you guys have seen it in analytical. Ricky hasn't. L-O-N-G-I-T-U-D-I. Longitudinal.
D-I-N-A-L. Oh, yeah, I noticed.
Oh, okay, all right. I wanted to make sure.
We just know what the hell it is.
So I'm going to knock off points for lunch.
Which one we were on? I didn't know if we were on the second to the last one or the last.
Yeah, we're way down here.
Okay, but I didn't
Two
know
types
to
of
spell
diffusion.
Eddy, that would have been
E-D-D-Y.
E-D?
E-D-D-Y. Eddy. Just like the name of a guy, I guess.
Yeah.
E-D-D-Y.
That's weird.
Anything up for spelling?
Oh, yeah. So that's why I want to make sure you get the spelling right. Eddy diffusion and longitudinal diffusion. Now, eddy was the one where it takes different paths. Well, what's longitudinal then?
Straight dragon.
Long way.
Has to result in things spreading out. This one is the type of diffusion you're used to thinking about.
People that
How long it takes to
Parallel to the.
I forget everything. That Christmas break was too long. It's the last thing
What does, if you have a,
that's me and Vince's.
I put a droplet of blue dye in here, right? What happens to the blue dye?
Yeah, it's
Spreads out from a region of what to a region of what? Greater concentration to lower concentration. Isn't there a problem with these peaks? Where is it the most concentrated? In the middle. So does that mean it's going to be diffusing in both directions? All directions. Yeah. All directions is going to be diffusing. Longitudinal diffusion. So that's just things diffusing from regions of high concentration to regions of low concentration. All right. What's an easy way to decrease the effect of each type of diffusion described above? Okay. Here's the uniform packing idea, right? How the uniform packing would help which type of diffusion? Eddy. So that would work for eddy. But is it going to do anything for longitudinal? No, so that's not going to be a good answer. Because it wants, what's an easy way, this one way that's going to nail both types. So eddy, uniform packing is good, but only good for eddy. Yeah. Make that column really long or really short, because you want to decrease. You could make the column really short. You could also do what to the flow rate of the mobile phase? Increase it. Now can you do that with this? With this setup, can you increase the mobile phase? Put it under pressure. You have to stick a balloon up here or something, right? And then pop off the balloon, dump in more mobile phase, put it back the balloon up, put the balloon back on. Okay. Now we're starting to get into, actually building something. But that's kind of where we're headed. So if you could really crank up that flow rate, that's what you're going to do. Because you can't be snipping this stuff. Okay. So that is about it.